Hi, my name is Taima Dahan. I'm a faculty member at KK in Japan, and this is me presenting to you the model AstroSage. AstroSage is a large language model fine-tuned specifically on astronomy, astrophysics, cosmology, space sciences, astroparticle physics, and so on. So all the astro topics. It is a domain-specialized LLM. So in this talk, I'll talk a bit about LLMs in general, and then I'll talk about how we specialized it. We trained on 250,000 AstroPH papers. Now, nobody has time to read 250,000 papers, but AstroSage has read them all. So I'll tell you about how we got this thing working. This talk is based on a couple of papers that are linked off of this page. We have an original CosmoSage paper and then two AstroSage papers. The talk will be scheduled like this, where we start with a bit about the AI revolution and why LLMs are so popular these days. Then I'll get into some of the gory details. I will talk quite technically about how LLMs work. Then I'll give some broad strokes, sort of tips and tricks on what I think could help you, hopefully, with your work. I'll then motivate AstroSage as a domain specialization. I'll talk about the model itself and how we trained it. And then finally, I'll end with some more thoughts about the field in general and what it's likely to do in the next couple of years. So let's start with the AI revolution. Now, what caught my attention in 2016 was this AlphaGo result. There was a show match between the world champion in Go at the time, Lee Sedol, and Google's AlphaGo. And AlphaGo beat the world champion sort of 10 years before time, right? People were saying for a long time that this had already happened in chess some time ago, but now it happened in Go, and people said it would take at least 10 more years, and Google surprised us with this one. I thought this was really cool and an amazing demonstration of deep learning in a practical scenario. Quite famous from this is Move 37 from the second game, and that's where the AI made a move that wasn't very human-like, but was very effective. So AI apparently, or deep learning, may be capable of generalizing well out of distribution in some sense. Then what really caught my attention in the LLM world, I was following this quite closely. At the time, I was already working on CosmoSage, and Anthropic released this model, Claude 3.5 Sonnet. Now, the text editor, or the IDE I was using at the time was Cursor. I started using them quite early on, and I was using mostly their tab autocomplete and their context-aware chat feature. So you could talk to an AI about your code, and you could also do tab autocomplete, so to complete a code chunk, either a line or even a couple of lines. And that was working very well, and I was very happy with Cursor. But they kept adding these features that I wasn't so sure about. These were features where the AI would sort of code autonomously, until suddenly Anthropic released their model, Claude 3.5 Sonnet, which unlocked this capability. Suddenly the model became good enough, and Cursor could do this. And so this unexpected unlock gave us agentic coding and vibe coding and so on, where vibe coding is defined as you're specifying what you want and you're checking the output and you're having a back and forth with the LLM, but you're never touching the code yourself. Whereas agentic coding just refers more generally about the process where the AI runs in a loop and calls tools working to make your code, but you're probably, in many cases, especially in scientific cases, still reviewing the code yourself. Now, this is a big business. So on the money side, this graph I thought was pretty interesting. You see here on the y-axis the annual recurring revenue. This is $1 billion. And you saw Cursor here in gray. So I was using them back here, and then suddenly they weren't making all that much money on this linear scale until suddenly the models got good enough and they really took off. And so they started making exponentially more money. And eventually, of course, Anthropic is not stupid. They see their models very good at this, and they put out their own, not exactly an IDE as a terminal tool, but they put out Claude Code, which you can see here, took off even sharper than Cursor did. This is incredibly useful for me. I would say in certain classes of tasks, this accelerates my work by a factor of 10, such as usually annoying stuff, messing with plots, doing a one-off debugging thing, debugging my environment, that sort of thing. Another, this is more as a joke, but there's apparently a Wikipedia page that I found as I was preparing for this talk, the Will Smith eating spaghetti test. So you see here, this is also based on deep learning. This is a convolutional neural network from 2023 using a so-called UNet. And in only 2 years, we've gone from this being, state-of-the-art Will Smith eating spaghetti to this, which is just incredible, right? The steam coming off of it as he lifts the fork and the little noodles flapping about. I mean, there's incredible physics kind of being modeled here, but nobody told the computer how to do that. It's all coming from training data. So very rapid progress. In July of this year, Google and OpenAI both achieved the gold medal at the International Mathematical Olympiad. These are pretty tough math problems. I like to think I'm decent at mathematics, but yeah, I could not answer this question under exam-like conditions, far from it. And the LLMs can. A couple of notes on this. One reason, perhaps, or one way you can see the LLMs might be good at this sort of task is the domain. It is amenable to verification. So LLMs are trained these days with quite a bit of reinforcement learning, which means that if you can create a kind of environment where the LLM can try many times and then sometimes succeed, and then we can reinforce those times that it succeeds, that allows us to train these LLMs better. And so these mathematical exam-style questions are very amenable to that sort of training. Another note on this is that the level of compute used for these problems for the IMO competition is quite high. These labs, we don't know exactly how they do it or for how much money or whatever, but we see that they're getting a level of intelligence that you don't get if you just make a free ChatGPT account. It's all very impressive, but what does history tell us? Well, history contains an interesting development in AI, which is the presence of these AI winters, where the hype cycle was such that people had too much hope, were sort of over expecting too much from this technology, and then the hype died down and there was a lack of interest for some period of time. So the open question is, given that there's a ton of hype in AI right now, will there be another AI winter around the corner? And I guess we'll see. I'll have some more thoughts about this near the end of the talk. But I do write, it is important to have a nuanced and precise understanding of AI's capabilities and limitations. All right, let's move on. Let's talk now a little bit about LLMs and what's under the hood, how they actually work. AI, machine learning, deep learning, these are all tools for beyond IID, beyond the assumption of independent and identically distributed variables. In traditional statistics, yes, we know how to do this in principle, but it can be very difficult to calculate. So to supplement these traditional statistical tools, we have these modern techniques, and these terms are not distinct. They have some interesting Venn diagram where machine learning is defined as an algorithm that learns from data without explicitly being told how to learn from that data. And deep learning is a subset of machine learning, which is any machine learning that uses artificial neural networks. Now, artificial neural networks look something like this. You might be familiar with an image like this, where this is the simplest perceptron algorithm, where you have a bunch of features or inputs, and you take a weighted sum of those features and then apply a nonlinear activation function, and then you get a scalar output. And the process of machine learning here is that you have many training samples where you have inputs and outputs that are matched. And what you do is you keep modifying these weights and this bias, the free parameters of the model, until you get good performance on the training set. An idea that came soon after was the idea of a multi-layer perceptron algorithm. Here, the input isn't connected directly to the output, but you have these intermediate hidden layers. These hidden layers are fully connected in the case of the multi-layer perceptron network. So you have here a neuron which is defined in the same way. So it's a weighted sum over its inputs, and those weights are programmable or are learnable, and then a nonlinear activation function. And I note here that the nonlinearity is extremely important, right? Because if you think about what it means to go from this layer to this layer, is that this is a vector of outputs that is, and here for each neuron you want to take a weighted sum over those outputs before you apply the activation function. That means that this, before applying the activation function, is just a matrix multiplication away from the outputs here. And of course, successive matrix multiplications by learned matrices are degenerate with just a single matrix multiplication. And so the nonlinear activation function is really, really important, right? Otherwise, it just collapses to a single layer. Now, here's a slide about architectures beyond the multi-layer perceptron algorithm. I think a couple of years ago, this would have been probably a more interesting slide to talk about. I would have talked about convolutional neural networks, recurrent networks, generative adversarial networks, and so on. But what's been happening recently is the transformer is just eating them all. So the transformer appears to be very useful in a variety of tasks, right? And is becoming pervasive, is taking over the roles of the previous one. So it's quite good for audio, turns out it's quite good for images, video, not just text, even though it was originally proposed just for translation. I write here the search for better architectures continues, which is true, and we'll see if another architecture comes along that takes over the transformer in some or in all domains. The history here is that deep learning really, it's an old idea, of course, but people really were, it captured the imagination, I think, a lot when AlexNet came out and beat this ImageNet competition by a lot. We then had the transformer take over, and then ChatGPT, of course, and the rest is history. Now, a quick side note, machine learning is a bit of an art, bit of a science. A Cornell professor here writes, changing random stuff until your program works is hacky and bad coding practice. But if you do it fast enough, it's called machine learning, and it pays 4 times your current salary. So, you know, the spirit of this message is, in my mind, that machine learning researchers are just trying a lot of things, right? They're trying out a lot of ideas. And since we have benchmarks, evaluations, we have ways of telling if the resulting model is good or not, we can keep the stuff that works and throw out the bad stuff. And the stuff that works, these recipes, they can diffuse, right? Because you tell your coworker about it, you might publish a paper, or in some other sense, you know, currently in the industry, you might get hired by another company. And the result is that good ideas spread around the community. And in some sense, the world, you know, with all the interest in LLMs that there is, the world is working on making this process of training and using LLMs better. And since the good stuff is being kept and the bad stuff is being thrown out, it's kind of like a gradient descent problem, right? Kind of meta-learning that the world is doing in this sense. So that's, I think, an explanation for why we don't know exactly why it works, but we know that it works. And neural networks, of course, are always hard to interpret, especially when you have all these layers. It's not so clear what's happening where. There's a field of people working on this mechanistic interpretation, and we'll see if good insights continue to come from that field. But there's a bunch of intuition, a bunch of empirical stuff. Like here I show some scaling laws, you know, as a function of parameters, your performance has some minimum, and so the locus of how large you should make your model, given a certain amount of compute, a certain amount of data, it's a recipe, right? It tells you what you should make your architecture in order to get the best results, without really a first principles or prescription on why that is the case. And there's similar scaling laws here for test time compute. Now, here's a little bit of PowerPoint I made to try to explain stochastic gradient descent. Some of you might already be quite familiar with that. The idea is that you have some big pool of data that may not even fit into memory, and you split that data up. Another way of saying that is you sample from that data without replacement. And so you split it up into these batches, and optionally you might reserve a small percentage of it as a validation set. Then the training goes like this. You take your model, which initially it has the architecture that you've decided on, and all of its parameters are randomly initialized. You then do a forward pass of this data through your model, which gives you the loss, right? The chi-squared or whatever the loss function is that you've chosen. You can then take the derivative of that loss with respect to your model parameters, and you can step in that direction of decreasing loss. And you typically step by some small amount, and the prefactor of the gradient, the step equals the prefactor times the gradient. That prefactor is called the learning rate. And you can do this with many batches until you run out of data. Once your data pool is exhausted, you have done one epoch by the definition of epoch. And then what you can do is you just rotate all your data back through again, and you continue training for another epoch. And so your loss curve might look something like this. I'm showing here two quantities. One is the training loss, which I just described. And then if you have kept a little bit of data aside, and this becomes your validation set, you never train on this validation set. So it's a bit of withheld data. And each epoch, it remains the same, and it remains withheld. So the model has never seen that data in some sense. And what you see is that as you do successive epochs, you will tend to find that the training loss continues to get better, but eventually the validation loss, while it continues to get better for a while, eventually gets worse. And this is called overfitting. And the prescription is to stop before you do too much overfitting, typically. Now, what LLMs do typically, or initially what they did at least, was single epoch training, where you just start here and you run your data through once. And so in this case, there's no need really for a separate validation set, since every batch of data is unseen data. It's statistically no different from a validation data set. Another note here is that LLMs don't really train using stochastic gradient descent. They train on some variation of that. So instead of just stepping towards the gradient, you might track the gradients a little bit better. And so Atom and Atom W are quite popular alternatives these days, among others. Let's talk about pre-training. LLM pre-training works like this. You make a neural network, and its inputs are a sequence of word pieces or tokens. So all the previous tokens in the sequence go into the LLM as at the input, and then the output becomes a probability distribution over what the next token might be. The way you run this in the forward sense at test time is that you can sample a token from that probability distribution over the next token, and now you can say, I have a new sequence. I have all the previous tokens, and I've added one additional token that I've sampled, and together this is the new sequence. And I can now run that sequence back into the model, and then again get the probability distribution over the next token, sample from it, and so on. And in this way, I can generate many tokens. This is called autoregressive because the model is fitting to its own previous outputs. At training time, you already know what all the tokens are, so you can still run the model in the forward sense. And for example, if you say the sentence is large language models are deep, blah, 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 then the input to the model is large language models are, and the output is some probability distribution over the next token. But you, of course, since it's your data, you know what the next token should be, in this case, the word deep. And so you can say, what is this probability? I'll take the negative log of that, and I'll call that my loss function. And I can do that for all the tokens in this sentence, and I can do it for all the tokens in this document, and I can even, not I, but some people can even do this for all the tokens on the internet, just about. And that's what this massive pre-training is. And you see here one of these loss curves that came from some very early experiments of mine, where the training loss initially starts going down as the model generalizes to better and better to unseen data. And at some point, I run out of tokens, so I have to start a new epoch, and then you see that the loss has become significantly lower all of a sudden, in that this data was already seen, and so some of it has been memorized, whereas the validation loss just continues to decrease. Then for the third epoch, you see another such jump in the training loss, but you actually see that the validation loss, its slope switches signs, so it suddenly starts getting worse. It's a good time to stop. Okay, let's talk a little bit about the GPT-2 architecture. This is an example of an LLM architecture, and I'll try to go over this in some detail. I hope this helps for people who are not familiar with the multi-layer perceptron network. This might be a bit of a slog, but hopefully it gives you some flavor. And for the people who already know all this, I'm sorry. I'm sure you've been asleep for a while. So this is the input sequence. I have here a sequence of tokens or word pieces, And at the output, I get a probability distribution over the next token. Now, what goes on in the middle, all of this part, is called a transformer or transformer block. And I stack many of those transformer blocks, in fact 12 of them, so that at the output here is not quite probability distributions over the next token. It's actually the input to the next transformer block, and so on and so forth. And it's only the final transformer block where what comes out can be transformed to the probability distribution over next tokens. So here's how it works. At the input, you take each token. You then look up its vector in the latent space in the embedding table or the embedding matrix. You add a little bit of positional embedding, and you set this vector aside as the residual stream. Now you do this calculation where you multiply by a learned Q, K, and V weight matrix in order to get these Q, K, and V matrices. You can then calculate this equation, Q times K, and you take the softmax. And what's interesting in these decoder-only autoregressive LLMs like GPT-2 is that you apply a mask in this before this softmax operation, where you're considering only the lower triangular portion of K-Q combinations. And when you do this, you sort of exclude a kind of correlations in one direction preferentially. So now this Q and K aren't just labels of totally symmetric quantities, they take on some meaning. And so the way people phrase this is that the query is what the token is looking for, the key is what the token identifies as, and the value is the information that token passes along. Now you get some output vectors, and in fact, this whole attention business, you can do it many times, 12 times in the case of GPT-2, and each time you do this, you call it a head or attention head, and you can combine the outputs of all of those heads using another learned matrix, which is the output matrix, into the input to the multi-layer perceptron block. This is that single feed-forward network that I schematically showed earlier, where what you do is you have a learned projection matrix to project this to a higher dimension, you apply your nonlinearity, and then you project it back down to the regular hidden space. Okay, and then at the output here, once you have all of these vectors that correspond to what token should come next, you can just apply the reverse, the embedding matrix in reverse in order to convert these vectors to some probability distribution with a softmax operation. I've left out a couple of details here, like the residual came out here and it goes back in later. There's some normalization questions like layer norm, batch norm, etc. And of course the positional embeddings, I didn't really go in detail about that. But I hope that that schematically helps sketch what GPT-2 looked like. And honestly, more modern LLMs don't look that different from this. Now that we have the architecture of the neural network, let's take a look at what a realistic training pipeline for a ChatGPT or a Claude or a modern LLM might look like. The caveat here is that the frontier labs don't tell us. They don't tell us what their training recipes are. And so this is just my best guess from sort of following the field and maybe listening to some interviews or reading blog posts or that sort of thing. I'm sure that this is perhaps slightly wrong in the details somewhere, but roughly this should give you an idea for how a true modern LLM is built these days, or is trained. We start with this internet scale next token prediction task. Now, one thing about this is that this is probably typically done at relatively small context length, because as you saw in the previous page, there's this query key, and you are looking at all combinations of tokens. So there's an n-squared scaling with context length. And so probably when you're feeding the entire internet through to train your network, you want to keep that context fairly small. And so there's probably some context extension phase that happens afterwards. There might also be other types of mid-training where you feed maybe the highest quality tokens through again. You know, not all tokens are created equal. Some tokens, like you know, a calculus textbook might be much more valuable in some sense, or you want the model to be much more familiar with them than a real estate listing from 1995, right? So after this training, you still have a base model, which only does next token prediction. It just continues documents from wherever you leave off. So now to make a chatbot, you do some SFT, some supervised fine-tuning, where you have conversations. You have user queries, assistant responses, maybe another user query follow-up, another assistant response, that sort of thing. And these are examples of how you would like the model to act. After doing this kind of training, you have an actual chatbot. And really the only thing that's different here between standard next token prediction and the supervised fine-tuning is that you have a bit of a mask where you're not actually training on the user tokens. You're only using those in the kind of forward sense, and you're really only training on the assistant completion. After this, you do some, I think they probably do some further SFT based on these reasoning chains. So the reasoning chain idea is that instead of having a user question, then an assistant answer, then another user question, is you insert an additional phase where the model gets to kind of think for itself. So you start with a user question, then you let the model talk to itself for a while. This is usually hidden from the user. And then you get the model to answer. And this kind of internal monologue type of deal is how they can do so well at this math competition you saw earlier, for example. And I don't think they start this from scratch. I think they start this with some examples of what these chains of thought should look like. So you do SFT on these example chains. Then the reinforcement learning stage comes. This is probably the hottest topic right now in LLMs, where you create a kind of environment where the model gets to try answering a question, and then you have a verifier. You can see if what the model has generated is correct or not. So the very simplest version of this is like a math problem or something where the answer is like, let's say, an integer. You can just say, did the model get it right or not? And if so, we'll reinforce all of the tokens that were in this chain of thought that came before giving the answer. If the model got it wrong, then we'll try to discourage the weights that led to those tokens. After this reinforcement learning, there's some more preference tuning and safety tuning that happens. This preference tuning is saying, for example, one way to do it is you would have humans rate model outputs. You would create 2 model outputs and you have a human say which one they like better. And then you can encourage the model to create such outputs. There might be special value models, or there are different ways of doing this. And safety, I mean, is hard to know exactly, but probably the companies are just really scared that their model will say something embarrassing or rude or you know, perhaps even illegal or something like that. And so they discourage that in some separate training phase. After this, you end up with the LLM. You might use that LLM directly. And I suspect some companies actually go through a separate route where they create a second LLM that's smaller, and they use distillation methods to turn this large model into a sort of student-teacher relationship where the large model is the teacher and the smaller model is like a student. And you don't just get the large model to create data and then train the smaller model on that data. You actually do something a little bit more sophisticated where you keep track of what this model thinks the probability distribution is over the next token, all the logits, if you like. And these are then used as a target to train to, and this is remarkably efficient. Okay, this is all I'm going to say about general purpose LLMs and how they're trained and so on. So let's now switch to some tips and tricks from me. This is a flowchart of how I choose which LLM to use. So everyone has their favorite LLM, I'm assuming. Mine depends a lot on use case. So I would first ask, do you need data privacy? And if so, you should probably run your own model locally so that you are really sure that your data is not going anywhere. There's a bunch of good local models out there. You know, there's GPT OSS, there's Kimi K2, GLM 4.6. I put QN here as my current favorite local model. They have a sort of 200 billion parameter model that's really good. Then if you don't need data privacy, go to one of the labs. You know, it's going to be a lot cheaper than buying your own GPUs, and they have typically systems built around the LLM which are quite useful, like tool use with Google Search or things like that. Then if you're coding, I would say, how sensitive are you to cost? So the most expensive model is GPT 5.1 Pro, and it is really quite good. Like, it has bailed me out once or twice from a very tricky bug that no other model was able to find. For people who are moderately cost sensitive, I really do like Claude Code. It is very good. It feels nice to use. GPT or OpenAI has Codex, which is their version of Claude Code, which is also quite good. I find it takes longer and it's a lot more verbose, but it is quite precise and it does get the job done, and it's cheaper. So if you're looking for this sort of $20 a month plan, I might currently recommend going with OpenAI. If you're not coding, then I have some mixed recommendations. For regular chatting, ChatGPT still remains very good. For writing stuff and kind of repetitive or mechanical tasks, Gemini 3 seems quite good, although I don't have quite enough experience with it yet. And there is a special place in my heart for Claude 4.1 Opus. On some kind of vague, underspecified tasks, I find it very, very good at discerning user intent and at having quite a wide knowledge base, it seems. That's my feeling anyway. If you don't want to take my word for it, that's cool. Here's a bunch of other ways to determine which LLM you should use. There's the traditional benchmark route. This company, Artificial Analysis, has their intelligence index where they run a bunch of these benchmarks. The idea is like you have a bunch of questions that are predetermined, and then you have a simple verifier. So in the simplest case, you might have a multiple choice question, and the verifier checks if the model selected the right choice. And there are slightly more sophisticated verifiers in here, and the sort of average over a bunch of benchmarks gives you this score from this company that you can just go to their website to look at the latest version of. Currently, Gemini 3 Pro is leading that, with GPT in second place. Then there's these other types of benchmarks like LM Arena. The LM Arena, the idea is that you can go there for free and use LLMs for free, where you ask your question and you get two different models to give their responses, and you just say which one you like better. And this is kind of a democratic way of figuring out which models are preferred by people. If I select just for the so-called hard prompts, I see that Gemini 3 Pro really is in the lead at the moment, with Grok 4.1 in second place right now, with error bars consistent with the Claude models as well. This is a kind of ELO score, preference score. So they always say ELO, they never mean ELO, but delta ELO of about 100 corresponds to some win rate of 64%, which is relatively modest. So really, these top models are all very good, and your preference might be more sophisticated than just picking the top one, although you can't go wrong with picking the top one most of the time. A couple miscellaneous things. One piece of advice I often give is try to separate what sets you apart from your coworker. What are your core proficiencies? What are you particularly good at? And I doubt the LLM is better than you at those things, at least at the moment. So I have wasted a lot of time trying to get LLMs to help me with my job, with my actual core difficult task that I'm trying to do. And typically they are not very helpful, and sometimes they cost more time than they save. However, for smaller things, like if you have a small gap in your knowledge or a small skill gap, getting LLMs to fill those gaps can be very effective. And at very common tasks, boilerplate stuff, LLMs are going to be really killer. They're going to be great, right? If it's an LLM amenable task, I suppose. Another tip here I give is try to improve your workflow. Spend some time making your tooling better. It's going to pay off in the long run, right? Top recommendation would be getting an AI-powered IDE if you don't already use one of the VS Code forks perhaps. Google just released Anti-Gravity, Windsurf is good, Augment Code is good. I personally use Cursor. There's a bunch of these out there, but they really are. Using one over using Emacs or Vim or Nano or what have you really is worth your time. Trust me. And don't fight the thing, don't fight the technology. Use it for what it is. So AI is just a tool. If your screwdriver isn't doing the job, then you're using the wrong tool for the job. So get the screwdriver that fits. So LLMs are, I see people doing things like complaining about something their LLM got wrong or how stupid it is and getting frustrated, I say, try not to argue with your LLM. I'm personally guilty of maybe having done this once or twice. Anyway, use what works for you, explore. If something doesn't work and you feel like it should work, write it off for now, but maybe come back in a few months when the models are stronger and see if it can do your task now, if you still need it done. Okay, let's move on now to AstroSage. Let me just motivate it in one slide. Here's the question, scientific question. It's a hypothesis. Even LLMs of modest size can be powerful if their scope is sufficiently narrow. Now, what do I mean by this? Large models are better than small models, typically, right? Models that are trained with more data and have larger parameter count. All other things being equal should give higher quality answers. However, what if we do a model that's very fine-tuned, in this case on astronomy? Can it outperform a vastly larger model? So this is the question we set out to answer with the CosmoSage AstroSage family of models. Here, model size, how narrowly focused the thing is, and maybe, under this hypothesis, maybe there are some contours of like equal capability or equal quality of answers. And could it be that our model that's highly specialized outperforms GPT-5 despite having vastly fewer parameters and vastly less training data? Okay, let's look at it. So here's the history of the project. I started off just kind of a hobby more than anything. I downloaded a bunch of papers. I downloaded the strongest open weight model at the time, which was Mistral, and I just wrote my own little fine-tuning loop in PyTorch to try to learn this technology a little bit. And I thought the outcome was interesting at the very least. And so I presented it at a conference, and I got talking to some people, and now we are working at a much larger scale, and we're working with a 70 billion parameter model. So who is we? We is Astro MLab, or Astro Machine Learning Lab. The person leading this group is Yuan Sen, and there's a bunch of contributors here that I briefly want to highlight. Yuan Sen has been very helpful with his leadership, but also running the benchmark and so on. Tirthankar, Emily, and Vanessa from Oak Ridge National Lab under Tirthankar's leadership have been fantastic for helping us obtain the computational resources needed. Josh is the one who created the benchmark. Alberto helped a lot with the data curation at the start. Aston helped with some general purpose benchmarking. I don't want to leave anyone's contributions out, but roughly speaking, we worked together. I did all the parts where I touched the model weights, the training stuff, but we work together closely, and we're a group of rogue Astro and NLP people trying to tackle this problem. Astro MLab is larger than this. AstroSage is just one project, and I'm showing here just the 10 people who contributed to AstroSage. Here are some of the ingredients that we needed to make this to get this off the ground. So time, computer time, human time, wall time. We needed some massive computational resources, and that was supported by Oak Ridge National Lab's Frontier supercomputer. We've used in total about 35,000 node hours at this point. If you look at how many GPU hours that is and how much it costs to rent a GPU, and you just do a sort of naive translation using commercial rental price, you might say that this cost $1 million to do. Now, it's probably a bit of an overestimate, but there are significant computational resources that went into AstroSage. The project took about integrated 6 months or so if you consider all the experiments and hiccups and so on. The wall time is really quite short because we use so many GPUs in parallel. In terms of software, the open source ecosystem is, I'm very happy with it. It's really quite good. GPU drivers, on top of that, you have your CUDA or your ROCm, maybe some custom kernels like Flash Attention, then a machine learning framework, in our case PyTorch, and then the LLM training framework, the sort of outer loop, whatever's holding the, feeding the data in and doing the actual training loop. updating the model weights and so on. So I started off with my own custom implementation and then switched to axolotl, which we used for both of our 8 billion parameter models. It's a very nice open source framework, but for the distributed larger problem with a 70 billion parameter model, we switched to Eleuther's GPT-NeoX. In terms of data, there's the pre-training data. This is dominated by papers from AstroPH, about 250,000 papers that we turned into a text-only version using OCR. We used a NuGot OCR for that. The supervised fine-tuning data set is a mixed bag. We got a bunch of data from Hugging Face, and we also created some of our own data. And for reference here, you know, a PhD thesis might be 50 kilobytes of text data or something, and we're talking here tens of gigabytes. So there's really quite a large amount of training data that went into this. The training takes 3 stages. We start off with continued pre-training. That's that next token completion loss function. And this is where most of the compute goes, the vast majority of the compute, and we think where most of the magic happens, where most of the new knowledge is added to the model. And we fine-tune from Llama 3.1 70B, Meta's model. After that, the model is still not a chatbot at all. It can just only complete sentences or complete documents. So we perform supervised fine-tuning, which trains the model to become a chatbot. It can do multi-turn, it has a good output style, it follows instructions, and we also, using SFT, train it to produce some of these reasoning chains where it can have a bit of an internal monologue before it answers. Finally, we find it very useful to do a bit of model merging. So we find that if you ask certain questions in certain ways, maybe very out of distribution, you can get some pathology. And so adding just 15% of Llama 3.1 70B instruct really helps with the non-Astro general purpose benchmarks and seems to have no cost on the actual Astro benchmark. Here's the loss history over time. We start off with a training loss on these AstroPH papers of the base model of around 1.3. That means a typical token has something like 27% probability assigned to it by the model. And then as we continue to train, you see that this loss decreases. You see no discontinuity here at the epoch boundaries, so there doesn't appear to be too much memorization going on. Same here. And then when we're done with continued pre-training, we switch out the data set for this masked data set where we're not training on the user queries, we're just training on the assistant completions, the supervised fine-tuning stage. You see here the slope changes. So the supervised fine-tuning slope is much steeper, and then there is a discontinuity at the epoch boundary. So it seems this data is quite different. You know, it's probably more predictable in some sense, more prone to memorization and quicker to learn than in the case of the continued pre-training. This is the learning rate, which we keep at Meta's value, and we anneal it in both the CPT and SFT stages. The model's available. It's up on Hugging Face, so if you have a GPU, you can download it and run it. In fact, our friends over at Raidermacher made nice quantized versions, so if you have just 40 gigabytes of GPU VRAM, you can run it. The inference is always expensive. You know, I don't just have GPUs lying around, but we did recently get a grant to have some kind of free inference available. So that's a work in progress as of the time of this recording. I hope very soon I'll have this up and be able to provide free inference to anyone, anywhere who wants to use this model, at least for a limited period of time. Now let's talk about this benchmark. This benchmark is 4,000 multiple choice questions on various domains in astronomy, astrophysics, space science, astroparticle physics, cosmology, and so on. Human verified, and we've been following this for quite some time, and we've been seeing the Pareto frontier move. As the labs release better models, we've been seeing these models go from a lower score to, as the new models come out, getting higher and higher scores. So we have here on the x-axis how much it costs to inference a model, and on the y-axis the score of the model. The base models that we start with, the Llama 3.1, are off the plot in terms of getting lower scores than these. But after our training, we get this roughly 81% and this roughly 87% for the AstroSage models. This AstroSage 8 billion parameter model is best in class. So in terms of the cheap models, it performs better than the other ones, which are below the axis break here. And our 70 billion parameter model performs just best. So they're even the very expensive models, 100 times more expensive almost, don't outperform our 70 billion parameter model, at least on this benchmark. And we tried to be really careful here not to cheat. So there are some papers that we did use to create the benchmark, and we actually left those papers out of our training data completely. So really the model can only learn about the topics that are covered in the multiple choice questions indirectly, if they were discussed in more than one paper, because there's no overlap between the training data and what was used for creating the benchmark in the first place. So we think this is a really fair test of the model's knowledge. Let's look at these general purpose. I'll skip over the details here, but this is a general purpose benchmarks. We ran several of these benchmarks on our 8 billion parameter model, and I'll just tell you roughly that this merging really does seem to help, and these red bars here are quite decent, thanks to injecting just a small percentage of Meta's instruct model. So somehow their SFT data that they privately have access to is probably indirectly helping us in that way through model merging. Okay, that's it about AstroSage. Let me do some thoughts about what AI might do in the next couple of years, and then I'll conclude in a few slides. The LLMs are getting better and better. So I have here, I just made this up, there's an axis here from very simple menial tasks to really your core proficiency. What sets you aside? What is something you can do, but the person sitting next to you cannot do? What are you good at? And I think of LLM capabilities as at first only being capable of menial tasks, and then slowly, like a wave, moving across this axis towards encroaching on the thing as researchers that we can do. So I just wrote some examples here down the bottom. Example of like wordsmithing. I have some English paragraph. I don't quite like the flow of it, where the commas are, and so on. And man, are these LLMs good at that. They really help me write better prose. It's still me doing the writing, but helping with the wordsmithing, LLMs are incredibly useful. So that's already happened, and that was true last year too, Converting between file types. I had to make a Will Smith movie that fit into PowerPoint for this presentation. And so I just use an LLM to do that because it knows all the syntax that I don't necessarily remember without looking it up, et cetera, et cetera, et cetera, until you get to this side where you have, for example, an LLM writing my emails. Now that's not happening, or not happening today. The LLMs don't have enough context. They don't understand exactly what I want. If I had to specify, it would be more work for me to specify than to just do it myself, and so on. And plus, I feel like in today's society, it could just be a little bit rude, to send somebody an LLM-generated email. So another example of something that's really near my core proficiencies is coming up with new ideas in my work. I don't rely on an LLM for this sort of thing, at least not yet. And hopefully there's stuff the LLMs never take over, like actual executive decision making, because that would put us out of a job. And maybe that's okay too, I don't know. But so this wave of LLMs is coming over, is starting from being able to do these menial tasks to encroaching on our core proficiencies. And we don't know. We don't know if this wave will crash or if it'll continue and maybe it will go way past this axis. We'll see. I like LLMs as just pure tools, but we'll see how far they get. And here's your choice. Your choice is where to sit on that wave. So the wave is moving regardless of what you do, but whether you want to be an early adopter and ride the front of that wave and get all of those boosts in productivity that LLMs can give you right away, or whether you wait for the tooling to get a little bit better and for more people to be using them and societal acceptance and so on, or some people enjoy pencil and paper, and that's okay too. The future of LLMs, we don't know where it's going to go. It could be that there is continued exponential improvement in some sense of the model intelligence. It could be that things slow down and we get something maybe closer to logarithmic or slowing down improvement of model intelligence. And here are some questions that I ask that I wonder about, that are going to affect how the future goes, I think. There's the question of reliability. Will LLMs continue to make stuff up and remain unreliable in certain ways? Will they go the way of the self-driving car, where there was a great-looking demo 10 years ago, but we still don't have streets full of self-driving cars? And it's slow progress. People are working hard and they're making great progress, but it's slow going. Maybe LLMs will do a similar thing. We don't know at this point, I say. Maybe LLM learning could be improved, algorithmic breakthroughs. So currently, if you give an LLM a textbook on calculus, the LLM will not learn calculus. If you give a human a textbook on calculus, they will work through the problems, they'll write out a bunch of math, they'll maybe ask their coworkers or their peers some questions, and at the end of that book, they will learn calculus. So the LLM needs to read 1,000 books. So there's something about the way these LLMs learn that isn't as good as how humans learn. And will LLMs bridge that gap? Will there be algorithmic improvements in the next couple of years? We'll see. We'll see. There's a couple of questions I have, like I think areas of promise are the idea of learning from experience. This is not my idea, but maybe the LLMs will learn in some continual aggregated way, where Claude Code is making a silly mistake and some guy across the world from me spots that mistake, hits the thumbs down button and says, this is not right. And then immediately that information propagates back to Anthropic servers. They figure out, without human intervention, they figure out the solution to this problem, and it gets pushed out in a way that all other humans will not encounter that problem anymore. Maybe it sounds like a bit of a dream, but it could be that there are algorithmic breakthroughs towards that get figured out in the near future. In terms of reinforcement learning, remember I framed this as you have a verifiable answer, and then you have the model's chain of thought. And if the verifiable answer is correct, you sort of reinforce, you enhance that entire chain of thought. It's not the greatest thing to do. There's the so-called credit assignment problem, where maybe some parts of that chain of thought are very relevant and really helped the model and get towards the answer, and you would like to reinforce those. And maybe there are some parts where it was not that great, and maybe the model got the right answer despite having written this silly thing in the chain of thought. And so maybe you don't want to encourage that so much. And so where to assign the credit essentially is unknown, and I'm hopeful that that'll be something that rapid progress will be made on very soon. There are some non-technical factors as well. There's the idea of an economic bubble popping. There's the idea of the hype cycle ending. Maybe people get tired of hearing about AI, or who knows. That's out of my expertise. Even in the worst case scenario, though, even if LLMs stop today at today's technology level, I think they will change the world in ways that they have not changed the world yet. So when I look at an area like education, I look at my own learning, how much enhanced it is by LLMs. If we could roll this out to everyone, in a way that, maybe I'm one of these early adopters in some sense of the sort of educational power of LLMs, and once this wave rolls over to everyone else, I think it makes a massive change in terms of learning efficiency. They understand by some definition of understand what you're confused about and how to clear that up. There's also some jobs that I think LLMs could replace at today's technology level, making the world more efficient. Now let me come to my conclusions here and wrap things up. LLMs are great currently as tools. I argue that they don't yet augment our core proficiencies. So currently the thing that sets you apart from your coworker, the LLM can't do any better than you. That's what I find, at least for myself. And they can dramatically speed up our research as tools, provided we invest a little bit of effort into using them, right? So investing a little bit of time in figuring out which LLM works for your particular use case, getting one of these AI-powered IDEs takes a bit of effort, but in my opinion is worth it. In terms of AstroSage, This is currently the top scorer out of all the models we've tested on our benchmark, despite being trained on a withheld data set. So meaning that the papers used to make the benchmark were not used in training the model. This validates our hypothesis. Small models can outperform big models as long as their scope is sufficiently narrow. The model weights are openly available, so anyone is free to use them. In fact, you don't even have to talk to us, right? That's the idea behind open weight. It's open for anyone to use. Although if you want, you're welcome to talk to us and join our efforts. We certainly are person power limited in the AstroSage project. And just to say, like, what is AstroSage actually good for? Now, I don't use AstroSage as a daily driver. It is not my LLM of choice during my normal workday. And the main reason is, it's kind of a few person effort. There's no large lab building a beautiful product around this. We haven't built tool use into it. And so a lot of the bells and whistles that modern LLM systems have, AstroSage does not. It's a bare LLM in that sense. But I do think it is very interesting to talk to, and I do recommend you give it a try, especially if you have some more theoretical or concept-based question that is about a specific topic in Astro that you find that general-purpose LLMs aren't very good for. You may find AstroSage good. I also think a future system like a multi-agent system where multiple LLMs talk to each other, AstroSage may find a particularly good role there, where it can be the sort of Astro expert in an ensemble of models. So thanks for your attention.